Hey folks. So last time we left off by solving this knapsack problem using the bottom-up dynamic programming approach. Today, what we're going to do is resolve it first using the top-down approach. And by doing that, what we'll see is where it is that this approach is more efficient, the dynamic programming approach is more efficient and requires fewer calculations than going through all 2 to the n calculation. It'll actually show how for larger problems, it's exponentially faster. It'll also show where it breaks down a little bit and where you might have some issues if the problem was set up differently with the weights. And why it is that still, um, in general, you can't guarantee a solution without doing all 2 to the n. All right. While the dynamic programming approach works in this case, and in a lot of cases, there are some cases where it won't work, and you're still stuck with 2 to the n. And so we'll see that. Then, after doing the top down, we will be able to solve it on the computer, and then come back and systematize it by introducing the Bellman equation and showing how you can kind of solve these problems in general quickly and reliably. All right, so let's get started. So we had solved this before using the bottom-up approach by splitting it into subproblems, where we said, okay, if we want to decide whether or not to include item 1 here, all we have to do is look at what the optimal is when there are 4 items left, and then we have the maximum weight is either, say, 8 if we don't include it, or 7 if we do include this item. And so then if we can solve the subproblem for when we have 4 items with either 8 or 4 items with 7 maximum remaining, then we can compare whether or not it's worth including this first item. All right. So let's draw it like we did the tree for the Fibonacci in first class. All right. So what we have to start with, maybe I shouldn't do this to be quite so big here. We have the number of items is 5, and the maximum weight remaining is 8. That's what we start with. All right. Now we have to decide whether or not we're going to include this first item. And the way we do that is we split off and say, I'll put down an N or a Y for don't include or include. And if we don't include, then we have 4 items left, and the weight is still 8. Meanwhile, if we do include, in this case, I'm going to do it for the first item here is what we're considering, then what we have is the number of items is 4 still, but the weight remaining is 7 if we do include. And then up here, we can say, okay, if we do include, we immediately get 6 in value versus 0. And then we'll have to add on whatever we get for these two, right? So if we had the solution, we could figure out whether or not to include or not. But right now we don't. So we're going to have to split on these and solve for each one of these recursively. All right. So now we can say, okay, with 4 items left, we can split that on either don't include or include. If we don't include, then we have 3 items left, and our max weight is still 8. If we do include, then we have n is 3 left, and our weight left is 6. Right? And then similarly, we can do here. And it's 3. You'll notice n is always ticking down by 1, because after each decision we make, we always have 1 fewer item left to consider. But the max weight is what's varying here. And 3 weight is going from 7 down to 5, because the second item weighs 2. And what we'll see is, of course, this is branching doubling each time, because what it's really doing is considering all 2 to the n possibilities. Include or don't include, include or don't include, include or don't include, and so forth. But at some point, when we're breaking this down, we should be able to see that we don't actually have to evaluate all 2 to the n all to the end possible branches, right? While if we continued all the way down, we would get all the branches. We'll see that some of them are duplicated and we don't have to do them. So let's go one more step here. So now at the third item, we either have n is 2 and the weight remaining is 8. Can't write this clearly to be 8. Or we could include the third item and our weight remaining will be 5 because it weighs 3. And then we can repeat that for these guys. And it's 2. Oh, I wrote down 3 here. Of course, that should be 2. Weight remaining is, if we don't include, that's still 6. Otherwise, it becomes weight of 3. And then we have, I was going to start writing down just the numbers because I'm getting a little bit tired here. 2 and 7, or 2 and 4. And then finally, we have either 2 and 5 or 2 and 2. Now here we already see, we're going to have to once again branch all these because we still haven't found this, because we can't just fill in a number here, right? We have to decide whether or not to include or not for the second time. So we're still going to go down that route. But just notice immediately here, actually, we have this guy right here and this guy are actually the exact same subproblem, right? Where in each case here, either we don't include, and then include the third item, and now we have only 2 items left with a weight remaining of 5, or we could include the first 2 and then not include the third, and we also have 2 items remaining with 5 weight remaining. So when we go forward and we solve this one, and eventually we figure out what the optimal amount of value and decision is for when you have 2 items, the last 2 items there with 5 weight, we can apply that same solution over to here. Just like in the Fibonacci where we said, once you've calculated Fibonacci of 5, we don't have to do it again for the other branches. We can just store that in a lookup and steal that and reuse it, right? Now, when you look at this, you might say, well, all right, Kevin, so sure, we got these 2 overlaps. This isn't really saving us that much, having to go through the 32 different branches, great. You've now saved a total of what? 1 out of the 8. But what we'll see, it's actually quite easy to show, as you keep going down the list here, the overlaps become the common thing. It's not just like 50% or overlapped or something. It's more like 99.99% are all just recalculation of the same thing under certain circumstances. All right. So let me so otherwise it does the same thing. We can keep going with this just like we did with Fibonacci. And then when we come up and we're solving it, we just store each one of these results where the number of items left and the weight remaining into a lookup table, and then or cache it. And that way, when we try to recalculate it, when we find it again, perhaps when we're trying to solve for the yes here, we can just reuse that solution. And doing this at the end of the day, we can also draw this real fast here, like with the table we had last time, where you have weight remaining, and then we had 0, 1, 2, 3, 4, 5, 6, 7, 8. And what we'll see here is that the difference between, you could actually store this exactly like that, where you have 0, 1, 2, 3, 4, 5. What you'll see here is that when we want to evaluate this one, which is right here, we're going to have to calculate that. To calculate that one, we need both of these. And then we can see right here, then to calculate the 4s, we're going to need 8, 7, 6, and 5. And then to calculate the 3s, we need these 2s, which include 8, 7, 6, 5, 4, 3, 2. So we're going to fill in all these. So we have to calculate all these. And then presumably after that, I'm going to presume that we probably need all 8 of them. So what you'll see here is that if we actually were to run this, which we will shortly, and we printed out the lookup table, it would be just like the bottom-up approach, except we didn't calculate any of these. Why? Because, well, we never needed them. To figure out the one question we actually had, it's impossible if you start off with the all 5 items and you're going from left to right. It's impossible to ever have only 4 items left to consider and less than 7 weight, because the first item only weighs 1. You include or not, you only have the 2 options. There's only 2 of these 9 possible weights will ever be filled out. So when you look at this, in theory, the top down could be a little bit faster just by virtue of not having to fill in the entire table. In practice, though, I'll say that I tend to find the bottom up approach runs faster. And that's because, first of all, it's just a little bit more, it's a little bit easier to just for a computer to just mechanically run through a line repeatedly, just run through lines in a nice little for loop versus doing a little bit more complicated recursion. And secondly, when you do it this way, it's usually a little bit easier to parallelize. So if you're starting to do parallelization, it can sometimes be much cleaner in the top-down approach, and so it depends on how you do it. Sometimes, if it turns out the top-down is results in a very sparse matrix here, then doing it with the top-down approach could be faster just by virtue of not having to fill in as much. But it really depends on the problem. You can try it out both ways and see which one works better for you. All right. So anyway, so now back to here though. So let's look at this as we keep going, right? So we're going to keep going and be done with it. And let's just consider really fast here. What happens if we had, say, let's say 30 weights and 30 values? Just for the sake of argument, let's say that. And let's suppose that our max weight is, let's say, so let's go back here. So let's suppose that we have, let's go even higher. Let's go 50 items. All right, this is a lot of items. And let's say that their weights can be anywhere from, let's make it a big number here. Let's go anywhere from 1 to 1,000, right? They all vary. Some of them weigh 80, some of them weigh 980. All right, let's just suppose that. So first of all, what is the maximum weight that all the items could sum up to? Well, if they all weigh 1,000 and we have 50 of them, that's a total of 50,000 for the weight. Max total weight of the items. Easy. All right. Now then, let's now suppose that we are down at, say, we keep going down. We start off with 50 items and we keep branching out, and now we're down to only 10. So we've gone 40 of the way down, right? We have to keep branching and branching and branching. How many nodes or will there be at 40 down, at a depth of 40? Well, that's easy enough. That's just going to be about 2 to the 40th. And what's that? Technically, it's going to be like 2 to the 39, but bear with me. So this guy is about 10 cubed to the 4th, which is 10 to the 12th. And so what is that? So 10 to the 3rd is 1,000, 6 is a million, 9 is a billion, and 12 would be a trillion. So about 1 trillion. All right, so we got a trillion nodes here. Just like over here, we have 8. By the time we get down to the 40th or so, we'll have a trillion. Okay. So, obviously it's going to be hard to evaluate all those. But how many of those, how many different weight values will there be? Right? So here, while we have 8 of the nodes, two of them are duplicates, right? There are actually 7 unique weight values. Well, here we just said, actually, if we sum up the first 40 of them, actually, I was doing for 50. So for 40 items, the maximum weight we could possibly have used up is 40,000, right? Or the maximum weight that we could even care about is 50,000, right? And so what it turns out is that let's suppose that, because first of all, if the maximum weight remaining is greater than 50,000, then the sum of the weight of all of them, you just put them all in, right? So the only reason why we'd ever care about the problem is if the maximum weight starts out at less than 50,000, because there we would actually have to make a decision. So if it starts out at worst case scenario 50,000, then by the time we've used up 40 of the items, we're somewhere between either 50,000 if we haven't included any items yet, if we chose no the whole way, or if we include all of them, then it will be 10,000. So it's somewhere between these two weights at most, and this is like the worst case scenario. And if that's the case, there's only around 40,000 unique possible values for the weights. So out of these 1 trillion nodes, only 40,000, and in reality, in practice, it's going to be far less unique nodes. So in other words, what you have is 999 billion, 999 million, 939.99. I can't count here. Why am I doing that? Just a 4. Just a 6. I'm sorry. There we go. So out of the 1 trillion of them, 999 million, 900 billion, 999 million, 960,000 of them are duplicates, are not unique. They're ones that would be overlapped. And so, you can also do this in terms of percentages. It's probably a little bit more reasonable, right? So you just get rid of 4 zeros there. And then let's see here. So you have 4 over, you have to divide by 10,000. And so 1,000 would be a billion. So that would be 1,000. So that would be 100 million, right? So only about that percentage of them are unique. And so, I'm not going to bother doing that right now. But, it's so it's 99.999996 or so are duplicates. All right. So this is why we're saving so much. Because while for this 5 one, there aren't that many duplicates. And if we keep going, there will be some inevitably, because you already see here, there can only be 9 unique values in this, 9 unique weights. And already if we branch again, we'll have, since 7 are unique, you're going to have 14. And so for sure, out of the 14, only 9 of those are unique. So we're already almost over a third of them will be duplicates by the next one. And you go over one more, and you'll have well over half will be. All right. So it quickly escalates because of this 2 to the power business. And this is why we're going to be saving so much when we're doing the dynamic programming approach. Now, when would this fail? Good question, right? When would this fail? Well, first of all, you can imagine that if the maximum weight and keeping it as integers, if instead of having 1,000, it was say, the weight could be in the trillions. Now suddenly the number of unique values you can have by the time you go down is still in the trillions. And at that point, there's a chance that you won't get many overlaps, right? It might be like this, where none of them overlap, right? But all the way down at the 40th, there's still no overlap. A more common case for this would be if you use, say, decimals for the weights, right? Now, of course, you have some level of precision, right? And that says how many, how many digits it can really take, how many unique values. But if you have real values going out to, say, 10 decimals or so, you're kind of going to get stuck. Now, as you go up very large, it'll eventually come in handy. But by that point, you have 10 digits, this table suddenly becomes, a billion wide. And it might still be a pain to calculate. All right. And so there are other techniques for trying to solve these, or at least ones for finding approximate solutions and such, and that you can use those. Or you can also say, okay, I'm gonna treat anything that's the same at say 3 decimals. I'm just gonna round it off there, and that reduces the size of this significantly. So there's a few approaches you can do to try to still solve this to at least an approximate solution using the dynamic programming approach, even for ones that you can't actually find the true solution because there's just too much uniqueness to the weights, right? So anyway, so this is the gist of it. Once we actually get these values, let's just quickly, because I don't want to bother actually going through the rest of this table here, this branching, I'll just fill in the solutions here. If you just have these two items and a weight of 8, you're going to get 17. If you have weight of 5, you also get 17. Here, I think it's just pretty much all 17. Anything less than 3 is 0. 4, you get 13. Otherwise, you're going to get 17. All right. So once we filled these in, now we can go back up and try to actually figure out what our decisions are going to be. So for the third one, its value is 10. So let me just quickly write down 10, 0, 0, 10, 0, 10, 0, 10. And the second value was 8. So we get those. And then, of course, these are all still no's for our policy. And then yeses. Right, so the story goes that if you don't include the item, you get 0. If you do include it, then you get whatever the value of the item is, but you have lower weight. So now looking at this, if we don't include the item, we get 0 immediately because we didn't include it, the third item. And then in the future, we're going to get 17, right? Versus if we do include it, then we get 10 right now and 17 in the future. So in total, you'll get 27 versus 17. Of course, we're going to choose this path and we're going to include it, and you get a total of 27. Right? Story here is a little bit more is you don't include it and you get 17, or you do include it and you only get 10 in the future. Right? You get 10 immediately and 0 in the future because you don't have enough weight for the big ticket item at the end. So you're going to choose not to, and you get 17 in all. All right, and then over here we'll choose this one to get 23 over 17. So we get 23. Here, we choose not to include, and we'll take the 17. Right? And so now that we have that, we can make this decision. If we don't include, we get 27 in total. If we do include, we get 8 right now, and then 17 for the remaining items, which is 25. So we choose not to include, and we get 27. Here we choose not to and get 23, or we do and we get 25. So we're going to choose 25. And then finally, right here, we choose not to and get 27, or we do and we get 6 plus 25, which is 31. And so we do include. All right. And then once again, now we have our solution. What we do is we take the right, so we include, then we include again, then we don't include, and to get the 17, so I didn't draw it, I think you go don't include and then include. And that's it. All right. So if we can just code this logic up in a recursive format, it should all work. All right. So let's go to the computer and actually do that. All right. So I already got the file ready here. So let's get going. Sorry, right now. Just need to pull that up there. I actually have some version I had written in the past there, so in case I run into any bugs, I can check and figure out where I went wrong. So let's see here. So first we have the weights, which are just 1, 2, 3, 4, 5, and we'll also try running this with a larger problem rather than just the small one. But first we'll do the small one just to make sure that everything's working all right. So the values were supposed to be 6, 8, 10, 13, 17. And then the weight and the max weight is equal to 8. All right. So Let's start trying to write this. So we'll say def knapsack, and this is, remember, this is going to be some recursive thing here. And so we have the number of remaining items. So we'll just say n, maybe n items if we want, and then remaining weight. Right? All right. And now what we're going to have to do is first calculate the value we get if we don't include, and then compare it to the value if we do include. Right? So let's see here. So we can say don't include value, no include value equals 0 plus knapsack. Now, we haven't quite fully fleshed everything out yet, so I'm just going to first start by writing it out, and then we'll go back through and try to fix things up. And then so if we don't include it, then we still have n items minus 1 for the remaining number of items, and we still have the same remaining weight. And then if we include it, then we get whatever the value is for that, which will be, I believe it's going to be values of minus n items. I believe this is along the same line of what we had done before. N items minus 1, gram weight, minus weights of minus n items, right? And so the idea of this is that it's the first one, we have 5 items, and so we take minus 1, 2, 3, 4, 5 for the weight, and minus 5 for the value. And then, and we have to subtract off that weight of the item if we include it, and we always have 1 fewer items left. All right, that's easy enough. And you have to say if, like I said, we'll still have to clean this up a little bit in just a moment here because this won't quite work as it currently is. If no include value greater than include value, then what do? Then we have to return no include value. Otherwise, return the include value. Normally, I just say return the max of the two if we're just returning the value, but I already know that in a few minutes we're going to have to make sure we add in not just what the maximum value is, but also the decision you make. All right, so we have to be a little bit careful there. All right, so once I add that, I'll have to add in, something like an n here. Maybe we can do that right now, actually. So we say don't include and the no include value, or we say we do include and we get the include value. All right. Now, if we're returning this tuple, we're going to have to be careful when we call recursively. You have to remember it's returning a tuple, and so we want to say of 0 here, of 1. Sorry, right? Because we want to grab the value, not the decision, right? When we call ourselves. All right, so that looks pretty good. We still have a couple problems here. First one that we need to fix is clearly the base case, right? So if n items is equal to 0, or maybe we can just say less than or equal to 0, just to handle if somebody throws in negative items for some reason. We can just return some empty thing, and you get 0 value. Right? So this will mostly work. We still have a slight problem, which is that we have not accounted for the maximum weight, right? And make sure you actually have enough weight available to put it in. So of course we can plop it in here. That's one way to do it. There's a few ways that you can do this. So one way is that, of course, we can say if there's not enough weight, just return immediately that you don't include it. But we will, so that's one way. The other way to do it is, and that's what we did in the bottom-up approach. I want to show you one other way, just because sometimes this is like the only easy way to handle it, which is that you can also say, like, if rem weight is less than 0, then return empty and then say minus, a huge amount. Now, this is not always a reliable way to do it, right? I just want to show you that you can do it this way. What will happen then, if you do it like this, is that suppose that we only have 3 weight remaining and this item weighs 5. Well, first of all, we can choose not to include it, and then we still have 1 fewer items and still the 3 weight remaining, which presumably we'll find some optimal value for. Or if we include it, then we get the value immediately of that item, but then we have to add on the value for this knapsack of where we have the remaining weight going from 3 down to -2, because we've included this 5 weight item. So now that we have -2 when we call this, we look at it and we say, okay, we have -2 weight remaining. Immediately, we kind of exit out, and maybe I should put it first. We exit out and you get negative like 1,000,000 or something in value. And so what will happen is that now this thing will have like a -1,000,000 in value. This thing will have some presumably positive value, and you always choose not to include. You'll choose not to ever put something in when you try to, because you get this huge penalty from going overweight. Now, the problem with this is that if suddenly I change my valuations to be in the trillions or something, I'm dealing with, I don't know, something like, or billions, something like spectrum contracts or something, and suddenly this penalty isn't large enough. So you'll have to make the penalty very large to make sure that it actually covers all cases. So it's a little bit unreliable. All right, which is why you might not want to do this, because this penalty only works as long as the penalty is actually enough to discourage the dynamic program from choosing that path. All right, because maybe adding that thing gives you more value than the penalty of going overweight. So I'll go back to doing it just kind of the standard way, which would say if we don't have enough weight, then we just for sure do it immediately, right? So we can say if rem weight is less than the weights of minus n items, which by the way, I should probably just put that into a variable, huh? We can just say weight equals weights of minus n items, and then we can replace this. And we can also replace it right here. All right, and so if remaining weight is less than the actual weight of this item, then we can just return the no and the no include value, which of course I haven't defined yet, so I got to move it up right there. So now we can see here, first we calculate the no include value. If it if there's not enough weight for the item, we just return that. Otherwise, we actually calculate the include value, and then we return whichever one is larger. All right? So that should work. Let's try running it. Python knapsack top down. Oh, well, it would help if we actually did something with this, right? So we can say print knapsack of an item of, let's see here, 5 or lang of values and the max weight. Right? It might be better to say n equals 5 here. Right? Just for that one's the number of items and all. Oops, and I definitely have that wrong. So let me just fix that up, comma, and there we go. All right. So now let's run this, and we see that sure enough, it outputs saying, yes, we include that first item, and the value is 31, exactly like we had on the board. Now, let's try doing this for some bigger problems, right? We promised that we could do this nice little overlap thing. So let's go up to, so let's change this around. And actually here, let me just comment this out so that way you guys still have it. There we go. Let's say n equals 40. And we'll just systematically do this. So what we'll do is we'll say that the weights are equal to list of range of n. So this way we just make a list of 1 all the way up to, or 0 up to 39. It doesn't really matter here. Values are equal to, we'll get some random values, so we'll have to import random. So here we'll just do a random.rand int, and then we'll draw some random, each one will be valued randomly from 1 to 100. All right. And so now we have n weights going from 1 up to 0 up to, say, 39, or n minus 1, and then each one of them are assigned a random value. And then we have max weight here. We're going to have to change this because with 8, obviously, we can't really fit very much. So what we'll do is we'll just say sum of weights over 2 or 4 is usually a pretty good number, right? So this way, we have all these items, we can only fit about half of the total weight that we have in front of us into our knapsack. So if we run this, let's run it. And of course, hopefully you already anticipated this, it freezes because it has to evaluate a trillion nodes. And we're not doing anything to actually store that stuff ahead of time in any sort of, in any lookup table or cache. Right? We need to do this memoization, otherwise we have to evaluate all the nodes. And so let's cancel that, and let's add in the lookup. And for right now, I'm just going to do the cache on the outside here. So we'll say lookup equals just some empty, we'll have to be some nice little empty dictionary, and we'll do this using dictionaries here. All right, so now what we got to do is we still have that constraint, but now we have to say if, and now let's think about this now. I think we'll use for our lookup to be the number of items remaining and the remaining weight as promised, as we were doing before, rem weight, together as a tuple. If they're inside the lookup, then all we have to do is return lookup of n items, rem weight. And so that'll be cool. But otherwise, we're going to actually have to calculate everything. And now we're going to have to be a little bit careful here. So we need to calculate the best result. So let's do it this way. So what we'll do is we'll say the best result is equal to not including it. And then we'll say if the remaining weight is less than weight, then we calculate the include value. And then if the include value is greater than the no include value, then we'll say that the result equals. All right. There we go. That's a nice little if statement there, which is easy enough to follow. What we do is, first of all, if there are no items left, then we just return that. If there's no items left, we get 0. Otherwise, if it's already in our lookup table, we just return that. We just short circuit out, and we don't try to expand out and evaluate that node. And otherwise, we calculate the weight. We calculate what our best is if we don't include it, and we set that initially as a result. If the remaining weight is greater than or equal to the weight, so if we can fit it, then we're going to go ahead and calculate the value we get if we include it. And if that value is greater than our current value, then we'll set the result to that. So by default, it will be this. Only in the case that we have enough weight and the value is bigger, do we then set it to instead say that we include it. And then once we do that, we just say lookup of n items, rem weight is equal to result, and then we return the result. Right? So that should now work. So now this will actually create the lookup table, and hopefully it will all work. Let's try running it, and voila. In this case, obviously we don't quite know for sure if it's right because we have this, well, first of all, it's a pretty big solution. So let's go back and try to change this maybe to a smaller one, and we'll try printing things out and take a look to see if it makes sense. It's always a good idea to do this. So we can print out the weights, print out the values, and then now one thing that's a little bit annoying here is that this still only gives us the total value here, which is 189, and that we include the first item. Well, of course, we're always going to include the first item because it weighs 0. But you know, what can you do? Well, and max weight here is going to be, I believe it's 7. So let's see here. So my bet is that we get 9, so that means 180. We see an easy way to add up to 180. Well, that's 110 plus 5 plus 50. That's no. Oh, well, let's see here. So it must be probably these 3, right? That adds up to 6, and that's 180. And then we add on the 9 there. So it's the first 4 items worth a total weight of 6 out of the 7 that we have, and we get 189. So that makes sense. Now, can we get it that way it spits out more than just the most recent one, but maybe all of them? Sure. First of all, we could just follow it along, which is something that I think I talked about last time and that you've implemented already, I'm sure. Well, we can also do it a little bit differently. One thing that we can do is we can say, we can move things a little bit around here where we say include result or no include result is equal to, what we'll do is we'll actually keep track of both the decision and also the value. All right. And the way we'll do that is we can say, we'll say no policy, comma, no value. I'm going to get rid of include just to keep things a little bit simpler here, just to keep the code readable, plus no value. Oh, plus equals 0, which is kind of clear here, where what we're going to do is that this is our decision, yes or no. And this was, and I should say, actually, it's not just yes or no. It's now we have to kind of put back on our recursion hats and think, which is that what we're going to pretend is that we've solved the subproblems. That way it spits out a list of all of our future decisions. Yes, no, 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 yes. And then also the optimal value, both the optimal decision and optimal value. So here the no policy is, if we don't include this item, what are all of our future decisions? All right. And then the no value is how much value we get there. Now, of course, we have to add on 0 onto that because we get no value from not including this item. Now, obviously plus equals 0 doesn't do anything. I only have this here just for conceptual purposes, right? And of course, I can add in a comment here, which I'll do before I upload it. All right. And so what we can do is we can say, now it's no plus the no policy, right? So now our result is take that whole policy decision for the future and just add a no to the front of it, because that's how we're going to handle this item, right? And then maybe maybe this is a good way to do it. There we go, right? So this is one option. The other one is that we get the value from including, yes value, I'll call it, right? Yes value and yes policy. We're going to need both, right? And then, so now we have that, and now we're going to make sure that we add on to the value. What was it? Values of minus n items, right? So now we have the additional, now we've added on the value there, and now we can say if the yes value is greater than, the no value in this case. I'm going to write a little bit different here, just because technically we add on the 0. I'm gonna do it. Let me do it this way, just to be clear here, because someday it might be the case that if we don't include the item, maybe we still get some value, right? If yes value is greater than no value, then result is yes plus the no policy. Sorry, plus yes policy, right? This is the future decision. If we include this one, what are all of our future decisions? And then we have the yes value, right? And then that should do it. So let's take a look at this, because now we've done the magic here. We automatically, for the base case, we return just an empty value, an empty thing. So that gives us a list, which will start prepending onto all of our decisions. And you'll see it's just like magic. As long as this gives us the correct, you just think of it as far as we've handled the base case here. And then uh, if assuming that the knapsack here does return the optimal future policy of all of our decisions in the future, and it turns out it's best not to include this, then we take that decision, all those future decisions, we prepend a no onto it. So now that is the correct solution for the set of n items. So if we have the n minus one, we get to the one with n items. And similar, if we can solve this subproblem with the yes, then sure enough, it will spit out just adding a yes into the front of it. So according to our theory of the subproblems, this should work. And I'm sorry, I don't know if some of that was unfortunately obscured. Hopefully not. But I know there's my video is down here, so I got to be a little bit careful. So here is, again, here's a different set here, where now it says yes, 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 no, no. All right, looks good. And in general, you'll see it's going to probably be skewed towards the lighter ones in general, just because they have the same expected value. And so, these smaller ones are typically a better bang for their buck, but not always. Here's a 5 here. And so here they end up including both 3 and 4 and 0. So let's try this out with 40. Obviously, we won't be able to probably just like look at it and say, here's all the weights. Here's all the values. Not a surprise, there's a lot at the beginning that you include. There's the occasional that you skip here. You see it has a value of 1, and this is probably the other one that you're skipping with a value of 1. Hard to say. Oh no, I think that's supposed to be a 15 and just wrapping around actually. Probably still not including the 15 though. And then you don't include the 19, and then you include the 92, and then you don't include a whole bunch, and my guess is this is probably the 83 right here that we're including. And then we include the 87 right there. So some of the heavy ones are still included, right? And it makes sense. It seems to match our intuition there. But it's interesting that a 37 with value 87 is included, but the 39 with 82, which is almost as good, obviously not quite as good, is not included. But anyway, so this works out pretty well. You can play with this. It works quite nicely. So now let's turn back to the board and talk about the Bellman equation, which tries to generalize this into a systematic approach to solving these. All right, let me just erase some of this. And then what I'm going to do is I'm just going to write up the Bellman equation, and then we'll see how what it turns into is exactly what we just did on the computer and on the board. All right. And how you can use this for any problem that you run into. All right. And what we'll do is we'll then change our code around a little bit to handle it for the Bellman, to write it in terms of the Bellman equation. So the general equation is v of x equal to the maximum for every action in the action set of the immediate value plus beta times v of the new state. All right, and I'll explain this one piece at a time. It's fairly straightforward. So v of x is just the value, right? So this was 31 in our case. This is the maximum value. So v is the value. And you'll notice that here's our recursion. The value here in the equation for figuring out what the value is, we have to call the value function itself. There's the recursion right there. right? So this is the knapsack calling the knapsack, all right? Then you have X, which is the current state. And so here, this is the number of items remaining and the weight remaining, right? Then what you have is A is our choice of action or our policy. This is, in our case, include or don't include. And it has to be in the member of this set. So what this says is, given our current state, there is a set of possible actions. In our case, you can think of it as, the set of possible actions are include or not include, but it actually slightly depends. Because if, for example, we have very little weight left, such that the item doesn't fit, our only choice in that case, we only have one action, don't include. We aren't allowed to try to include it if there's not enough weight. So this is where it says it depends on the current state. We may not, your choice of actions might depend on the state. In our case, if we don't have enough weight, we lose out on the possibility of adding it. All right. F of x comma a is the immediate value. I should have two m's there. Immediate value. So this is the value you get by taking that action. So when we choose to not include, we get 0 in value from that item. If we choose to include, then we immediately get whatever value that item has for us, right? So if we include the last item, we get 17, right? That was at 0 or 17, right? There it is right there. The beta here, in our case, is not relevant, but this is the discount rate. So when you're dealing with things involving time and stuff, you can say, okay, if in the future, if I choose not to take, this one has a value of 6, and the future stuff, the remaining stuff, I might have some value, say like 0.9 or something. So that way, the future value gets 10% less value because I have to say wait for it in the future. Here, we aren't really actually dealing with time. This is mainly for time, temporal problems and such. In this case, since it's all making decisions at the same time, it's not like these future ones have somehow, it's not like we're actually physically waiting in time, which is somehow costing us. And so we tend to ignore, so for a lot of our problems, we're going to end up ignoring this, but for a lot of problems, it's very important to include it. A lot of common problems that run into in Bellman equation. And then finally, T of x comma a is the transition. So what this says is, given our current state and whichever action we choose, we go to some new state. All right, so this is just saying, all right, if we choose not to include this one, now we have one fewer items and the same remaining weight. That's our new state. If we do include it, then we have 4 remaining items and one fewer weight. So we go down to say 7. That would be our new state, right? And this function says, given our current state and our action, what's going to be our new state? All right, so now that we've defined this, we can actually see that this is actually pretty straightforward. What this right here says is, we're going to look through every different one of our possible actions, and we're going to take the immediate value plus this future value that we're going to be getting recursively based on our decision, right? Plus the future value based on our decision. And then what we're going to do is we're going to evaluate all the different possible decisions, and then we're just going to take the best one of them, right? So this is just saying, is it 0 plus the future of, say, 27? In the case of the first one, I think it was like, for this actual problem, for the very first step, it was, do we want to get 0 right now by not including, but in the future we'll be able to get 27 by taking the 3 and the 5? Or do we take the immediate value of 6 by including it, but then we only get, say, I think it was 25 in the future by including, I have to look at it, probably the 2 and the 5, right? And then it comes out being, oh, yep, 31's better. So because out of our 2 options, don't include or include, the best one, the maximum, is the 31. So we spit back out the 31. And so that's all it is. This is the Bellman equation. And it's just doing exactly what we've already been doing, but just writes it in a formula. All right. But what's nice about it is let's actually try taking our problem of our knapsack and writing it out in terms of the Bellman equation. All right, so just really fast, I'll do it on the board, and then we'll quickly plug it into the computer, and then we'll call it a day. All right, so first of all, our state is going to be our number of remaining items, or n items. I'll just write down n and the maximum weight remaining, right? That's our current state. The value function is just our knapsack. Our action, or our set of actions, I should say, is going to be one of two things. Either just include yes, or no, I'm sorry. We can't include if not enough weight. Which of course we can just say if weight of I is greater than, here we go. We're going to say if weight of I is greater than the maximum weight, right? Or weight of minus n, I suppose, given what we're doing here, right? So this is using the current state. We can grab out which item are we looking at and also what the current remaining weight is. And then it's either no or yes if the remaining weight is enough, right? So we'll just say otherwise. All right, so this is the formal way of saying if we don't have enough weight, our only option is to not include. And if we do have enough weight, then it's don't include or include. F of x comma a is going to be equal to one of two things, either 0 if no, if a equals no. If our choice of action is to not include, then we get 0 immediately. Otherwise, it's just going to be our lowercase v. This is a different, this isn't the total value here. I'm talking about the lowercase value there. Value if a equals y. And then our discount rate is 1. Right, I'll erase a little bit up here so that way we can fit it. Our discount rate is 1. And then finally our transition, g of x comma a, is what? So if we don't include, then it's just going to be n minus 1 with the same remaining weight if a equals n. Otherwise, it's going to be, and maybe I shouldn't be using curly braces. Maybe it should just be parentheses. There we go. Otherwise, it's going to be n minus 1 and then weight minus the weight of the item if a equals 1. Right? And that's it. So now we've defined it all. So once we've defined it, we should be able to just plug it right in here and be set. All right, so let's try doing that. All right, so first I'm just going to copy everything over here into, we'll call this knapsack Bellman stuff. All right, so I'm going to quickly, once again, I already have the solution someplace, and just in case I screw anything up or forget something I want to know. So let's see here. All right, and once again, we'll still need the lookup table and stuff, so we'll still have that. So all we have to do is we just define each one of these one step at a time into our function. So we can say first def possible actions given our current state, and we'll have to define the state in just a moment here. Maybe we should actually think about that first. Let's start out with a state just being the tuple. Later on, I think what's really, really valuable doing is importing name tuple and including that. So I'll probably do that really fast. I'll do it in class, one of the two. We'll see, depending on how I feel at the end of this. So what we do is we say item weight equals state of let's just also note right here, maybe we should quickly write this down. State equals n items, comma, remaining weight, right? We could do it as a, yeah, I mean, we'll stick with it like this, and I'll show you why it is that you really want that named tuple. It'll make things easier. So we have to take weights of minus state of 0. What a pain. Right, so that's how many items are remaining. We take minus n of that, because state is 0 should be the number of items, right? So we get that item weight, and then we can say if item weight is greater than state of 1, which is the remaining weight, remember, then we return just no. Otherwise, right, that's if we don't have enough space in it, that our only possible action is to not include it. Otherwise, it's going to be no and yes. Right, that's going to be our possible actions. And right now, I'm not going to include the, for this case here, I'm just going to do the optimal value and not the whole thing. So we'll have to just make sure that it works. You know, I mean, obviously, now that we've done it once, you see how you can easily add in what the actual correct include, non-include are. We'll just include the maximum value, which should be 31 here. All right. Next, we'll put in the transition function, which will be the next state. And so it has to take in our state and our action. And we already said on the board there, if action is a no, then we return the new state, which should just be state of 0 minus 1 and state of 1, right? So we keep the same number, and we just reduce the number of items by 1 and keep the same weight. Otherwise, in this case, the action will be yes, that we do include it, then we have to return state of 0 minus 1, and then state of 1 minus weights. Maybe I'll write down item weight equals weights of state 0 minus. Well, again, this is not a great way of doing it by having to refer to the negative of the, yeah, that's kind of garbage. As we go through it, I think next lecture, next class period, I don't think there is going to be a next, I'm going to skip 1 week of lectures, and instead, next class, we're going to go through and talk about how to clean up code, use classes some, make better use of how you pass things into functions and such to make this a little bit cleaner code and easier to read. All right. And so, anyway, minus the item weight. So there's our next state function. Easy enough. Either we don't include or we include. And then we have the immediate value. State, comma, action once again. And if action is equal to no, then return 0. Otherwise, return the item value, which is values of minus state of 0. Right. Let's see here. So now we have our gamma function, the possible actions. We have our t, which is the transition function. We also have our immediate value function, f. And now we just need to write the core recursion. So let's write the Bellman. So we pass in the state. Oh, and you know, we do also still need a base case still, right? So that's why we'll have if state of 0 is less than or equal to 0, just return our 0. If the state is in our lookup, then we will just return. It's sometimes worth actually reversing it a little bit and saying one thing that I kind of like doing sometimes is, and I think it'll look cleaner. Do you want? I'll hold off on doing this right now. Let's stick with it as we have it. Return lookup of state, and then I'll quickly go back and just quickly switch this around just to make it a little bit cleaner. And then what we got to do is we still have weights of state of minus n of 0. All right, that's the weight. But now we actually have to write this up here. So let's write this. Let me skip this and write it up as with the Bellman. The Bellman equation says that we're supposed to do uh, a maximization over all the different possible actions, right? So luckily there is a function in Python called max, and you can pass it in a list. So what we'll have to do is make a list where we say for action and possible actions of state. So what we've done is that this part right here is just going to say that we're going to do a for loop over all of our possible actions, and then we're going to calculate how much value we get in it, and then we're going to return whichever one is the maximum of those, right? And that's easy enough. It's just the immediate value of, and by the way, we can just delete all this, right? Immediate value of state comma action plus our beta, which is just 1, which I'll just put down 1 there just for the sake of argument, times the knapsack, right? We have to call it recursively, of the next state, or the transition function of the state and the action, right? And that should do it. Supposedly that'll all work, right, according to the Bellman equation. All we've done is just taken the Bellman equation, plopped it in the code, right? Over all of our possible actions, so for each A and gamma of the state, get the immediate value of the state and the action, plus beta times the V, right? This is our V, knapsack is V here. V of X is equal to the maximum over every action in the gamma of X, F of X comma A, plus beta times V of T of X comma A, right? And so in theory, this should all work. Let's try it out. Obviously, we don't want to run knapsack top down, but next knapsack Bellman, and we get a error. Oh, knapsack takes 1 positional argument, but 2 are given. Oh, that's my bad. Right here, remember, our state now is supposed to be a tuple. I was passing it in as n comma remaining weight rather than putting them in a tuple as 1 argument. And it's still no good. Let's quickly take a look. So it says function object is not subscriptable. Let me see here. And for action and possible actions of oh, I'm sorry. This should be, of course, a change surrounding that guy into that guy. There we go. That's a function. I use little square brackets like I would an array. That was just a typo. And we still have another typo. Let me take a look at this one here really fast. Knapsack. Oh, that's my mistake. We set the optimal value, but of course, we need to actually return something, right? So we have to say lookup of state is equal to optimal value, and then return optimal value, right? Or alternatively, we say lookup of state, right? And this is why what I was about to say is that one thing that I like doing is rather than just having this if it's in the lookup, return it. What I like to do is say if it's not in the lookup, then we need to calculate it, right? So what you do is that if it's the base case, just return 0. If it's not in the lookup, then we quickly calculate it and then store it in the lookup. And then after that, we return the lookup. So if it is in it, we just skip over this and return the lookup. And this I find is a little bit slightly more intuitive, where the default, where we always return from the lookup table. And it's just that if it's not in the lookup, then we have to do this extra step of calculating it first. All right, and we run this and we get 27. Oh, that's not good, is it? Wow, I must have a bug. Oh, no, I don't have the max weight here of 7. That's why. Max weight equals 8. Max weight's supposed to be 8. There we go, there's 31. Exactly as promised. All right, so one thing that you should look up, which will make things a lot cleaner, is if you use from collections import name tuple. What it does is, I'll quickly pull it up here. Let me see here, named tuple. It's really nice in Python. What you can do is, here's a little example. If you have like a point, X and Y, what you do is you can define our point to be X and Y, have X and Y. And then what's really nice about it is that it's still just like a normal tuple. So if you make one of these points, you can say P of 0, P of 1, and that works just fine. But you can also say P dot X, P dot Y. So what it lets you do is kind of give names to the first argument and second argument or third argument, however many you have. You can name them. So for example, we could do N items and remaining weight is what we could name them. And then rather than having to say of 0, of 1, which you have to then try to translate back and remember what that means, instead you could just say something like state of, dot and items or something like that, right? We could say that instead, and it's doing the same thing behind the scenes. It's still just a tuple and everything, but now it's much easier to read. Where instead of state here, it's remaining weight, right? So now it's item weight is greater than state dot remaining weight. So it's easier to remember than the of 1, of 0 business. So that's something I recommend you try doing. You can look up how to use the. I'm not going to do it right now. You can look up the name tuple, and then you can start trying to include that and see how well it works. All right. So that does it for today. Like I said, in class, we'll just go through several examples, defining the states, defining the possible action, defining the immediate value, and the state transition function, and we'll implement a few. And then next week, we'll go through and try to start trying to, what we'll do, we'll take a little detour and do a lot of cleaning of the code and such, and talk about how you can write cleaner and better code that's a little bit more reliable. We'll probably talk a little bit about testing even and profiling. So it should be a lot of fun. All right. But otherwise, there's going to be no like video record lecture. We're just going to do it all in class the following week. All right. So anyway, so I'll leave it there, and I will see you guys in class.